Test. Test. Okay, so let's get started. So we are going to continue our discussion from last time on fault tolerance, and today we look at the problem of consensus, specifically in distributed settings. So I will talk about what is consensus first of all, and then most of the lecture is going to focus on two very uh, popular methods to achieve distributed consensus. One is called paxos and the other is called RAFT. Okay, so we'll look at how both of these things work, and that will basically end the chapter on fault tolerance. And starting next time, we will start looking at web application and the World Wide Web, and come back to some of what we had discussed early on about web services and things like that. Okay, so let's start with consensus. But before we do that, I did want to finish that one slide I did not get to last time. So if you remember, we were talking about distributed commit in the last class, and I presented this approach called two-phase commit. Okay, and what two-phase commit does is it's essentially a way for a coordinator and a set of nodes to agree on whether to commit an operation or not commit. Okay, so that's the problem of distributed commit, and so it's an all or nothing, which means that either everybody commits or no one commits. You cannot have a case where a subset of the nodes have committed and others have aborted. So that's something we don't want. So we want to ensure a consistent decision for every commit operation. Okay, and we looked at two-phase commits, a voting protocol. The first phase, the coordinator asks everyone to vote whether to commit or abort. You get the votes, okay, and then you decide based on the vote whether what to do. If everyone votes to commit, the decision is to commit. If even one node votes to abort, then the decision is to abort. Okay, and the problem with two-phase commit that I talked about last time was when the coordinator node crashes. Okay, and if all the other nodes are sitting in the ready state waiting to hear back on the outcome of the first round, which was the whatever they voted, then you are deadlocked. You cannot make a decision independent of the coordinator. So the coordinator is also one of the nodes that has voted. So you actually don't know coordinator's vote. So the rest cannot make a decision. In paxos, what we'll look at today, we'll see that the majority is enough. Even if some nodes have disappeared, the rest of the nodes can actually make progress. In two-phase commit, you cannot. Okay, we'll relax that a little bit and talk about three-phase commit, where we can deal with coordinator failures, but both of these will still have a problem of if the network gets partitioned, okay, and some set of nodes never participate, you still cannot make a decision. Okay, but this one, at least this enhancement of two-phase commit, which is called three-phase commit or 3PC, okay, as the acronym, gets over this problem of a coordinator crash. And the way we do this is we add one more stage to the voting phase. So now there are three phases, which is why it's called three-phase commit, not two. Okay, so what happens is the same as before. There are two figures here. One is the coordinator, which is the first one, and then the second one is essentially the node that is participating in the election. So everyone starts off in the init stage, and the coordinator starts off round one by saying, vote on whether to commit or abort this operation. Okay, and all the nodes are going to vote, and then they are going to go to the ready state waiting for the coordinator to tell the nodes what was the outcome of the election. Okay, coordinator is going to get all the votes and do the same thing as before. Okay, if all the votes say commit, everyone has to agree to commit. Then you go ahead and say the outcome of the vote is to commit. Otherwise, you basically say abort. Okay, so let's say the vote, there was at least one node that asked to abort. The coordinator is going to send out a global abort to all the nodes, and then it'll go to abort, and then all the other nodes that were sitting in ready, they'll get a global abort and go to abort. So that's the straightforward case. Okay. But now, if all the nodes agreed to commit or voted to commit, then what the coordinator is going to do is it's going to send out a commit, a pre-commit actually, or prepare to commit to all the nodes. So they will go and sit in the pre-commit state. They won't actually commit. They've just been told of the election's result. Okay, so they know that the decision is to commit, so they'll go into a state called pre-commit and wait for the next step, the third round to start. Okay, so you will essentially end up here, and then once the coordinator has heard from all the nodes that they have moved to pre-commit state, then it's going to tell all the nodes saying, now actually go ahead and commit. Okay, so commit happens in this case in two steps. The first step, you're informed that the decision is to commit. Okay, and then the second step, once everybody has been told of that decision, you are actually asked to go ahead and commit. Okay, as opposed to two-phase commit, where in one step you are told saying the decision is to commit, and then you went ahead and committed. Here, you are going to do that in two steps. Okay, and what happens as a result is you added one more stage to that entire decision-making algorithm, and in doing so, we can now get over the problem of coordinator crashes. Remember, the issue in two-phase commit was if you finish the first phase, you voted, and you're stuck in the ready stage. Okay, and the coordinator never returns the result of the vote. You could not make any progress. You are stuck there because you don't know what the coordinator did. Okay, so now what you can do is if everyone is stuck in the ready stage, it's actually fine to go ahead and abort, because at best, if some nodes have heard from the coordinator, they're either in abort or they're in pre-commit. Nobody's actually committed, right? So it's still safe to go ahead and say the coordinator has crashed. You can go ahead and abort if everyone is stuck in ready. If any node has actually entered pre-commit, then other nodes can say the coordinator actually told them that the result of the election was to commit. So at least one node is in pre-commit, so everyone can then enter pre-commit and make progress. Okay? So essentially, you don't have any. So the important thing here is there is no state in that state transition diagram where there are two final decisions in one go. Okay? Each one leads you to only one decision point. So wait can only go to abort or pre-commit. Pre-commit is not a final decision. Only abort is a final decision. Pre-commit goes to commit. That's the only decision. So there is never a doubt which path to take. Okay? Because you can always make a safe decision in this case if the coordinator has crashed. So that's the basic idea of how you can get over a coordinator crash. Okay? It does not still solve the full problem, because as the next slide, in the next two slides, we'll discuss what are the issues with two-phase and three-phase commit. Despite solving the coordinator crash problem, there are other problems. Okay? So that brings us to today's lecture, which is going to be how do we get agreement, okay, which is the same problem as before, but we don't have to wait for everyone to vote to make a decision. It's still going to be a voting protocol, but you just want a majority vote, not a vote from the entire group. Both two-phase and three-phase commits, everyone has to vote. No one can make progress, even if one node does not vote. Okay? So if a node crashes, doesn't vote, or something like that, you're going to be stuck. If the coordinator crashes, you're going to be stuck. What we'll do is we'll relax that property and said, you don't need everyone to vote. Let the majority decide. So even if some subset of the nodes are down, you can still make progress. Okay? That's what is going to get us to consensus. But there are two things we will look at. Okay? First is, how do you actually make agreement in the presence of crash failures? And the other is, how do you do this for Byzantine failures? Okay, so let's assume there are n replicas. Okay, so if you are only worried about crash failures, the problem is of replication and how to deal with failures is simple. In the normal case, you assume that the incoming requests are sent to replicas, so you're just using them for load balancing, not for essentially replicated decision making. And if one replica fails, someone else takes over their load and you're done. You never actually send a request to multiple nodes and ask what the result is, because it's just crash fault tolerant. You will never get an incorrect output. All that is going to happen is if there's a crash, you get no output. Okay? So you can always have another replica take over that failed replica's job and reprocess the request and get you an output. So this is a very simple case. We don't really need to worry about it. Okay? The other problem comes when you essentially have problems like Byzantine failures or other types of failures, not just Byzantine failures. But in this case, this is a second technique. Each request is sent to all the replicas. In the previous case, each request is only sent to one node, so you can load balance. In this case, each request is sent to all the replicas. You collect the responses saying what actually is the response that you want to send, and you have to then, a majority has to agree, okay, for you to make a decision. In 2-phase and 3-phase commit, all of them have to agree. Okay. In paxos, a majority have to agree. So essentially, you will send a request to all the replicas, vote, and make a decision. That's the second case. Okay. So in the context of paxos, even if some of them have failed, that's fine. You can, the rest can take over. Now, if you have Byzantine failures, which means not only are you voting, you are actually producing bad results. Okay, that requires a set of techniques that go beyond what we will talk today. Okay, we will talk about normal consensus today. In normal consensus, you're only dealing with crash faults. Okay, nodes are not maliciously trying to change the vote. Okay, nodes are simply trying to either send a response or they have failed, so you don't get a response at all. Okay, in Byzantine consensus, nodes can actually try to send a bad response to confuse the vote, and you still want to reach agreement. Okay, that's called Byzantine agreement or Byzantine consensus. In techniques like blockchains or cryptocurrencies, you essentially have to use Byzantine consensus. What we talk about today will not work because there are bad actors that might try to confuse the problem. Okay, but we'll start with standard consensus, not Byzantine consensus today. We'll really not go into Byzantine consensus, but at the very last class, we'll come back to blockchains and I'll talk a little bit about it, but not in the same level of detail we'll go into here. Okay. So with that, let's now talk about what is consensus. Okay. So consensus is simply a problem of getting a set of processes to agree on something. Okay. What you agree on doesn't really matter. It could be you want to agree on whether to commit a transaction. You want to agree on who's the leader for this group. You might want to agree on has this broadcast been received by all the parties, atomic broadcast. You might want to agree on is the lock available or not. Okay. There are all kinds of decisions you have to agree on, and everyone has to have the same consistent view for the system to work. And those are just 4 examples that we have already seen. But it could be any other thing that you want to agree on. You might want to send a database query to a set of replicas, and you want to agree on what the result should be. Okay? Or you send a web request, okay, a REST request, and you want to get the same response. Okay? So all of these require you to have essentially consensus. Okay? And consensus, as I said, can means so there's consensus and there's Byzantine agreement. Problem of consensus is where the nodes can fail and not produce a result. In Byzantine consensus, the nodes can actually produce bad or malicious result, and you still want to reach agreement. Okay, so we'll only talk about the first one as I talked about. Okay, there are 4 properties we want when we talk about standard consensus. Okay, the first one is actually called agreement, which is every correct process. Okay, correct as in it's running. Okay, we're only worried about crash failures or fail stop failure. So every process that's up agrees on the same value. That's called agreement. Okay, so you can't have some processes saying 2 + 2 is 4 and some other process, no, I think it's 5 or something like that. So if you are operating correctly, you agree on the same value. Okay, termination essentially says every running process agrees on some value. Okay, that means that you have, so if you are up and running, you actually have to agree on something. You cannot not agree on something. Then you will not reach consensus. Okay, validity says that if all the nodes propose a value, okay, V, then all correct processes are going to decide that that is the value that they want to agree for whatever you are trying to agree on. Could be whether to commit the transaction, what the number ID of the leader, anything that you're trying to agree on. Okay? And integrity says every correct process decides at most one value, and if that somebody must have proposed that value. Okay, they are kind of related properties, but these are all the properties we really want. But the most important one is at the first one, right? So you actually want to agree on the same value. Okay? That's the first and most important property in consensus, that you cannot have some processes say, okay, the leader is 10 and the other processes say we agree that the leader is 5. Then you just elected 2 leaders. That doesn't work, right? Or some processes say the lock is free, other processes the lock is in use. So you can't have processes agreeing on two different values. So agreement is fundamental to consensus, but all the other properties are actually needed for a protocol to work correctly. Okay. Is this clear? Any questions? Yes. Okay. So agreement and termination. So essentially, agreement says every correct process will agree on some value. Okay. And termination says that you will actually terminate, the protocol will terminate. Right. So you could agree on nothing. That's still, so you did not disagree. If I don't participate in the agreement, I'm not disagreeing. So you can have agreement by doing nothing, because fundamentally agreement says you cannot disagree. Termination says that you actually have to agree on a real value. Okay? This says there shouldn't be disagreement. This says that you actually have to converge, you have to finish and say we agreed on a real value, not that we are sitting doing nothing, so there's no disagreement. No disagreement is agreement at some level. So you won't want that property to be there, right? So those two come together at some level. Any other questions? So that's a good point. Okay. So just to go, before we get to paxos, we'll see why two-phase commit and three-phase commit we already looked at are not going to give us some of those four properties. Okay. So first thing is, both of those in the absence of, or they have some problems when there are failures. And the problem is, first of all, there are two kinds of, in a distributed system, there are two very high-level properties that are important to keep in mind. One is, and they're nothing to do with consensus, is general properties. One is called safety property. The other is called liveness property. Okay. Safety property means nothing bad happens in the system. Okay. Liveness property means something good happens in the system. Okay. So that goes back to the question that was actually asked in the previous case. You can have agreement by doing nothing because I'm not disagreeing. So that's a safety property. Saying nothing bad has happened. Okay. But you want liveness as well. You don't want a protocol that does nothing and say, okay, I got agreement because there's no disagreement. You want a protocol to do something useful. Okay. So that essentially requires termination. So here, this is the safety property. That's your liveness property. Okay. So in any distributed system, you want some combination of safety and liveness. Safety just prevents something from going wrong. Liveness actually gets you something useful. Okay. Because often you can get a safety property by not doing much at all. So you want both of those properties. Now in two-phase and three-phase commit, you have the safety property, because if you remember, if the coordinator crashes, all the nodes are just sitting there waiting. Okay, they don't actually make a decision. So you don't actually end up with nodes making different decisions because everyone is just sitting there doing nothing. So that's a safety property. Because the coordinator has crashed, they don't know, other nodes don't know what to do. But liveness, there is no liveness in there because you are deadlocked waiting for a decision. So you want both of those properties, which is why we'll get to paxos. Okay? So in two-phase commit, the coordinator must be up for you to have both the liveness and safety property. In three-phase commit, you can actually deal with coordinator crashes because I just showed you this extra pre-commit stage. Okay, but network partitions are still an issue. The network is partitioned into two. Okay? Some nodes are in one half, the other nodes are in the other half. The coordinator is never going to get all the votes because fundamentally the network is broken into two. You cannot communicate across the partition. So you will not get all the votes. So you cannot make progress. Okay? So network partition still cause an issue in three-phase commit, which we'll deal with in paxos. In paxos, if the network is partitioned such that there's a majority on one side, that majority can still make progress. Because in paxos, the majority vote is what matters, not everyone voting. Okay. So we are going to take the idea of three-phase commit. Okay. Paxos will also be a three-stage protocol, but we'll just try to get to the majority rather than everyone. Okay. And see what we can essentially do with it. Okay. And here the majority simply means the nodes that are responding to the coordinate. Okay. And they have to be strictly greater than n over 2. Okay. The rest are failed nodes, so they don't even respond. Okay. So either a node responds or it just failed. And if the majority of the nodes are responding, okay, then you can make progress. All right. So with that background, let's talk about paxos. Very fundamental problem in distributed system. This is basically doing fault-tolerant agreement. Even if some nodes have crashed, okay, how do you get to agreement? Okay. So I will describe the protocol on the next slide, but here is just some higher level properties. You can deal with node failures in paxos. Nodes can crash. You can deal with network failures. A network can be partitioned. You can deal with network delays, arbitrarily slow network where nodes are not responding within a timeout value. All of those can be handled. You cannot deal with Byzantine failures. The node is sending bad results. The paxos may not converge, okay, or it may converge to a wrong value. So no bets. All bets are off if some nodes are Byzantine fault. But so long as they're only crashing, you can actually get to consensus. Okay? So many use cases, as I said, same as last time. You can want to elect a leader. You want to agree on whether to commit the operation. You want to decide whether a lock is available or not. All of this you can do with paxos-based protocol. Okay? The idea is very similar to three-phase protocol or three-phase commit protocol. Okay, one node, but more than one node can be a leader if you are actually in two partitions. But let's just say there's one leader. Okay, so you have to first choose a leader. The leader is going to propose a value and is going to ask node, do you accept or not accept? Okay, and the nodes can say whether they accept or not. If the majority decide to accept, okay, then the leader is going to say, this is the value that we all agreed on, and then it will basically ask everyone or convey to everyone that that's what we agree. Okay, so multiple phases. But if there is disagreement, okay, which means that some nodes basically don't agree, then you will have to essentially retry until all nodes are going to agree. Okay, so we'll see how that works. Now, again, the technique itself was proposed by Leslie Lamport. This is probably the third or fourth time we are encountering some work that Lamport actually has done. And I mentioned long time ago that Lamport is also the person who developed LaTeX. And LaTeX actually means Lamport's tech, if you know what that acronym means. So he's done a lot of work that is quite influential in distributed systems. Okay, so anyway, so it was independently proposed by Lamport and also Barbara Liskov, who's a faculty member at MIT. So both of them came up with this idea. Then a lot more work has happened since then. And today it's used in many different systems. Okay? There is Zookeeper, there is the Chubby locking service. Google has the Spanner system, very large-scale distributed systems. They all use paxos. And if you remember, when we were talking about Google's Borg scheduler, okay, which is what led to Kubernetes, I said that all the Borg masters, they are using paxos to keep track of which containers have been placed on what nodes, because that state has to be kept in a consistent manner. All the Borg masters are replicated 5 times, if you remember. They keep this state using paxos. So everyone has the same state of what the cluster looks like, which nodes have what containers, and so on. Okay? So in any case, I think widely used protocol for a variety of reasons, but let's look at how it works. Okay? So we want both safety and liveness property. Safety property simply says all nodes agree on the same value, okay, and that value was proposed by some node. Okay, because you can always say, I develop a protocol where the answer is always 0. Okay, that's going to always reach agreement because that's a trivial protocol. You'll never disagree. Okay, but that's not useful, because if you want to actually agree on some real value, you want some node to propose that value and agree to a value that was actually proposed by a node. Okay, which means that's the actual result of the computation. Those are our safety properties. Liveness property says if less than majority of the nodes have failed, okay, which means more than n/2 nodes are up, okay, then you will actually converge. You will get a result. Okay? But liveness is not guaranteed if there are nodes failing in the midst of running the protocol, in which case that round will fail, and then the coordinator will retry with a smaller number of nodes. But so long as still a majority, it's okay. Okay? So nodes failing in the middle of the operation, you are not going to get a result. Okay? So there's a steady stream of failures, you will not get liveness. But if some number of nodes are failed and now the set of nodes that are up is stable and a strict majority, then you will get a result. Okay? So those are all properties that paxos will give us. Okay? Now we'll see that the protocol is straightforward, but proving its correctness is actually much more involved. That's not very different from 2-phase and 3-phase commit, because you have to argue what will happen if there's a network partition right in the middle of some step, or if some node does not actually provide a response. Okay? And then you have to restart the protocol. Or if the leader crashes. Okay? You have to then elect a new leader and restart the protocol. But in all of those cases, you have to make sure that your safety properties are met, that you won't have some subset of the nodes agreeing to some value, some other nodes agreeing to some other value. You can't have that happen. Okay? So proving that actually is the hard part, which we will not get into proofs here, but I'm going to just show you how the technique actually works. And it's not very hard to understand at a high level. Okay? So there are 3 slides on this, but the idea is not that hard. So essentially, there are 3 types of nodes in our system. Okay? One is the leader, which is also called the proposer. The leader is the one that's going to suggest a value, okay, and try to get all the other nodes to agree on that value. So the leader could be saying there's now a new real leader for some other process. We elected a new leader. Okay? This is leader of paxos, but you may be electing a leader for something else, like you want to run the ring locking protocol or something like that, right? So you will. So that's the one that's going to propose a value. Okay? Acceptors are the ones that are voting. They accept or not. So they're voting yes or no. Okay? And then there are followers nodes, which are called learners. We just want to hear what the outcome is. They don't actually participate, but they want to use the outcome to do something. Okay? So in some sense, if you, let's say you have databases, the database itself would be a learner. It just wants to know what query to run next. Okay? The set of nodes are deciding, here are queries coming in. Let's decide which one we to run next, and everybody agrees that's the one to run next, and they all execute that next query. Okay? So in this case, so systems like databases will be our follower or learner. Okay? So the idea is the leader is going to propose a value, and it's going to solicit acceptance. It's going to say, do you accept this value or not? Okay? And acceptors are nodes that will either say yes or no, depending on what the value is and so on. We'll look at that in just a moment. And then so long as everyone is agreeing to it, the value gets chosen, and then you get the results of the vote. Okay? Very similar to two-phase commit, where you ask whether to vote or commit or abort. You get the results, and then you tell everyone what the outcome was. Here, rather than commit or abort, you say this is the value V for whatever it is that you're trying to get agreement on, and then everyone is going to vote. And if majority vote, you're done. You can basically convey those outputs. Okay? So that's the high-level idea, but there are some details I'm going to give you on the next slide. So there are 4 variables each node has to maintain. Okay? There is NA and VA. So essentially, there are rounds in paxos. So you may take some number of rounds. Each round is numbered. Okay? And so that is called the proposal number or the round number. Okay? So you will start with the first round, say here's the first proposed value there. Our next round thing is the next proposed value. And so rounds are going to be numbered. So you have to, each node has to keep track of what is the most highest round it has participated in, because the node might crash and come back up. Many of these things can happen. So you keep track of, this is the most recent round I've participated in. And if you voted for some value, you have to keep track of that value as well. Saying I participated in round 5, and I said the new leader is node 10. So you have to keep those things, track of those things. Okay? NH is the highest round number seen so far. Okay? And my N is my proposal number in the current paxos, which means that if you are actually participating in a round, that's your round number as well. So I'll explain how all of this works on the next slide. So there are 4 variables. Okay? The first phase, okay, it's called the prepare phase. This is where you're asking everyone to vote. Okay? So first, a node is going to decide to be a leader. Okay? And then it's going to propose a value. So the node is going to first pick a round number, okay, that's greater than whatever it has seen. Okay? So it has to pick a new round number, because you could be a new leader that's already been, and the election, the paxos may already be in progress. Okay? If it is the first one, you'll start with round 1. But if already there are some rounds and this is a new leader, you have to pick a new round. Okay? So then you send a prepare message saying, here's a new round number, okay? And you send them to all the nodes, okay? And then say, ask them to vote on some value. Okay? So upon receiving this prepare message, what a node can do is, if this is less than a higher round number you've already seen, okay? Just the proposer just picked a low round number, you can just say reject. I think I've already seen a higher round number, so I'm not even going to participate in the vote. But let's assume this is a new round with a higher round number, then you actually vote at this point. So you can essentially suggest some value that you want. Okay? And so you can send that value back to the. So remember that in this case, you don't pick an arbitrary value and suggest, because we said either the nodes operate correctly or they don't run at all. Okay, so you can, so if you since you operate correctly, you will pick a valid value. You're not going to pick some bad value and send it back. Okay, you can also send null. Okay, so initially you can send null and wait for someone to first propose a value. If you don't want to propose one, you will, but some node has to propose some value for this to converge. Okay, so if everyone send null, you're not going to get anywhere. Okay, so you send either a value that you accepted so far or you send null. Okay, in phase 2, which is the accept phase, the leader is going to hear back from the majority. Then it's going to look at all the values that came back. Okay, if they were all nulls, then the leader gets to pick some value and say, here, nobody has a value. I am going to suggest a value and you can send one. But if they all suggested a value, then you can pick any one that it wants. Okay, so that essentially you will get some values back and you can pick the one that you want. Typically, they'll all match. Okay, but sometimes you might have nulls from someone's and non-null message from some other ones, and you can pick one and then you can send that back saying, I will ask you to accept the value v and send a non-null value to all the nodes. Okay, but now if you do not get a majority, you are going to essentially say this round failed. Okay, I asked for a vote, majority didn't vote, so I can't make a decision. You stop and then you restart with a new round saying this round has failed. So hopefully the next round some nodes have recovered and you can get somewhere. Okay, is that clear? Okay, now once in phase 2, once the nodes actually hear from the value, what you can do at this case is you can still just say accept or reject, because you can say that if this is a lower round number, you'll say reject. Otherwise, you're going to say, okay, I will take this non-null value that was been proposed, okay, and then you will have to send an accept in this case. Okay, so essentially, it's the goal of the proposer or the leader to get everyone to agree on a non-null value. Okay? And so long as any one node in the system chooses a value, we'll assume it's the right value, that is going to propagate. It's either going to start from the leader and it tells everyone, or one node proposes it, it comes to the leader and it tries to then tell everyone saying, this is the value to be agreed on. Okay? We assume that the value v is always the correct value. There's no Byzantine fault here that you are trying to agree on an incorrect value. Okay, is this clear? All right. So there's actually in the phase 3, you tell all the other nodes saying that we all agreed on this value v and this is what you should. Okay, so the 3 phases, the first two phases are the more important one. So I'm going to very quickly review what I just said. So step 1 or phase 1, okay, the leader is going to ask all of the nodes to vote. Okay, that's called the prepare message. So he's going to say prepare to vote, and he's going to send a round number. Okay, so long as if the round number is invalid, which means a lower round number and has already been seen, you say I already participated in a higher numbered election, so I'm not even going to vote. You reject. But so long as the round number is valid, you get to send back a value to the leader. Okay, you can also send null saying I don't have a value to propose. But if you've seen a value in a previous round, you can say, I saw 5 in the previous round as the new ID of the leader, so I propose 5. Okay? So the leader in the then gets all of these votes. Okay? If everyone said null, then it has to pick a value. Otherwise, you will never converge. You ask everyone, they say null, and you don't do anything. And it gets to pick a value. And if they voted, some voted null, others voted non-null, you can pick the right value, which is a non-null value, and tell everyone saying, let's agree on this value based on the outcome of the election. And then you send that to everyone. Okay? And then other nodes at that point have to take that value and say, okay. And then third phase, everyone is told what the outcome of the election. Is this clear? Okay. So that is paxos. There are lots of properties which I'm actually going to skip here because we are not going to go into proofs. But here is a very simple pictorial depiction of what has happened in paxos. So you will see there are 3 nodes, 0, 1, and 2. The one in the middle is the leader. Okay? These 2 nodes are essentially our acceptor nodes. So first, it's going to send prepare messages saying prepare to vote. Okay? You will see that both of them have sent a null value, saying I don't have a value. I'm going to send back an OK, but I don't have a value to propose. Okay? So in this case, the leader picks a value val1, okay, and then says, let's all agree on val1. Okay, and it sends the same one, and then both of these nodes get val1. They say, fine. They will send an OK, and then you say, we decided on that. Yes, that's a very simple protocol. You could have also had a case where maybe one of these nodes, instead of a null value, returned that val1 to the leader. The leader will say, fine, you gave a non-zero value, we'll take it. Because remember, any non-zero value is assumed to be a correct value in this case. There's no Byzantine fault. So long as someone has a result, we assume it's the right result. So one of them had sent a val1, you would get that, and then pick that one and tell everyone. So somebody has to propose the value first. And so long as you propose it, will propagate through the system and everyone will agree. Okay? And you only need majority agreement in this case. Is this clear? Okay. So many issues here which have to deal with, and the paxos does work. Network partitions. If you have the network gets split into two, okay, we'll assume that there are odd number of nodes. So essentially, there's one side will have majority, hopefully. Okay. If you have even number and you split it, you might have equal number, so there's nobody has majority. But if you have odd, then one side will have majority, and that side can agree. The other side, even if you pick a leader, that leader will not make any decisions because it is not hearing back from a majority. So it can ask for a vote, but it will just keep failing. Okay? So the minority can actually never agree on something, even if there's a leader and they all vote for something, because the leader will not agree. Okay? So that one is okay. You can have timeouts where the leader has asked for a prepare message or something like that, but the responders are very slow to respond. Okay, the leader can just time out and say, I didn't hear back. And so long as it's still heard from the majority, you're okay. Okay? And if the leader itself doesn't respond in a timely fashion, okay, the other nodes can pick a new leader, saying the leader itself has failed. Okay, it's not actually providing an answer to the rejection. Okay? You might actually get a situation, or you shouldn't, but you can have a situation where there are two leaders, okay? Because maybe there was a partition, there's one leader on one side of the network, there's another leader on the minority side of the network, and then the partition goes away. Okay? And there are suddenly two leaders in the system. You have to be able to deal with that, and then only one of them can actually be the real leader. Okay? So that part also has to be dealt with. And leader failures is the same problem, where you have to actually pick a new leader as same as a slow leader. Okay? So all of these have to be dealt with. I didn't actually show you some of the subtle details of what happens in all of these cases. But when you actually implement paxos, you got to deal with these issues. Yes, question. Okay, question is, in a network partition, why can there be two correct values, right? No, so I didn't say there are two different values that are correct. All I'm saying is there's a network partition. Okay? You essentially, let's say, I mean, the example of a network partition is UMass loses internet connectivity. The rest of UMass network is functional, and the rest of the world internet is functional, but now there are two different networks, right? So long as you're running paxos and there's a majority on one or the other side, that majority can make a decision. All I said is the minority cannot make any decision or cannot even agree on a value, because the leader, if you elect a new leader in that minority, that leader will never get enough votes to make a decision. So you are never going to get 51% of the nodes responding, because there aren't that many in your side of the party. So even if there was a value, you would not agree to it. It's not like you're producing a different value. You will just sit there waiting for a majority to respond, which will not happen until the network partition is healed. Okay? That's what I meant to say. Okay. So what I'll do next is talk about a different way to achieve consensus, which is called RAFT. Okay. So paxos is not an easy protocol to understand and implement. Okay. I gave you the high level idea, but you can understand the subtleties of all kinds of failure cases that have to be dealt with in your code. So you want to make sure your code actually makes does not get you to something that is incorrect. So it's actually not very easy to implement. So many researchers decided that that's not the way you want to do consensus, but we'll come up with a different idea for consensus, and we'll talk about one called RAFT. Okay? So RAFT is called understandable consensus. You can decide whether it's understandable or not, but it's a little easier to explain. Okay? RAFT uses a different idea. It uses an idea called state machine replication. Okay? It's called SMR. What SMR means is that each machine is going to keep a file called a log. Okay? And all the operations you want to perform are going to get added to the log in append-only order. That's what you do to a log. You can append. Okay? And what you're trying to have agreement on in this case is that the order of entries in the log is always the same across all the machines. Okay? So the real reason you use RAFT is your replicas that are receiving requests. Requests may be received out of order at different replicas, but all replicas have to execute the request in the exact same order, regardless of the order they were received. That goes back to a database example where you are receiving multiple queries. Some queries might be received at one replica first and later at another one, but you have to actually perform the transactions in the same order. So the idea is first you will run RAFT. RAFT will essentially append these queries to the file, the log file. Okay? And the idea is that the log file should be ordered the same way across all the machines. So the queries will appear in the same order. And once you put them in the log file, your database or whatever application it is, it's simply reading the log file and executing whatever is the next request in the log. So it's a list of requests. Okay? And you're doing request ordering by putting them in a file. And the file, so long as the files look the same across machines, they will appear, requests will appear in the same order. And then your web service or database is simply reading this file and just executing requests. Okay? So consensus in this case is simply the problem of trying to agree what order to perform. So this is an ordering consensus problem, not a general consensus. Paxos can agree on many different things. Here, we are simply trying to agree on ordering of requests. Okay? And we are trying to do this by writing them in the log, and there's a log at each replica, and you write them in the same order. Okay? And you can still have problems like there's a network partition, nodes crash, so they may miss requests, etc., and you still want consistency. Okay? So it's basically a question of I give you 5 files, and I try to send you requests, and you have to write them to the file in the same order, always. Okay? And how do you solve that problem? Okay? So this is called a replicated log. This is why it's called state machine replication. So you are going to replicate a log, and so long as the log is consistent, the nodes that are reading the log and executing requests also end up in a consistent state. Okay? So here's how it's going to work. We'll again elect a leader. Okay? The leader will essentially get the requests first. Okay? And then it will try to send the request to all the nodes saying, write this request or append this as the next request to your log file. Okay? So it's going to send them requests saying, here's the next request, append it, and the next request, append it. So long as all of that is happening successfully, you will get the log in the same order because you are receiving a stream of requests from the leader. Okay? And that's a FIFO stream, and you're just writing that. Okay? Problems come up when leader crashes, some nodes crash, and then they come back up. They have a log where they missed some requests that was appended to the log while the node had crashed and so on. So we then want to make sure that log is repaired and made consistent with the rest. Okay? So here is going to be how it's going to work. So I'm going to show you 2 examples. First, we'll look at the single server log, and then the next one will be the replicated servers. So here is a set of servers. Okay? Each of them has a log file. Okay? We'll assume in this case, the log is essentially making updates to a simple key value store, which is like a hash table that's shown here. Okay? So this is the actual state of the database or your key value store. There are 3 entries in the key value store, X, Y, Z. There are certain values. Each request is going to modify a value of X, Y, and Z. That's all that requests are doing. Okay? So you get a request, you'll say change X to 6. Or you get a request and change Y to 7 or something like that. Okay? So what is going to happen is, in order to, before you perform that update, you first have to write that request to your file, and then the file has to be consistent across all the nodes. and then some other process is going to read that file and make them. And here is our log file that you will see, and you'll see it just as a set of operations that are in there. So there's operation saying set x to 3, and there's another one saying set y to 2, then one that says set x to 1, and you just got one that says set z to 6. So first you write that to the log, and so long as everyone commits to that log successfully, only then can you take it and actually put it there. Okay? This is a single machine log. Okay? Here you will see a replicated log, because there are many replicas. That was just one machine. All of these replicas have a copy of that hash table. Okay? And so each one is getting the request, and they have to make that same request, perform requests in the same order. So you all have to, each of these have to keep that log. Okay? So when a new request comes in saying set z to 6, they all have to be written here first. Okay? And once they're all written successfully by a majority, not everyone, right? Because it's same problem. You can't assume everyone can do it. So long as a majority of them do it, a strict majority, okay, then you can go and perform the operation. That's the high level idea. Is this clear what we are trying to do? We'll look at details next. What is a replicated log is clear, right? Okay. So here is how we are actually going to do things. So there are many approaches. There's a leaderless approach for consensus. There's a leader-based. RAFT is going to be a leader-based approach. Okay? The leader is the one that's going to first get this operation. Okay? So this one leader here is going to say, get this request saying, change the value of z to 6. Okay? And that's the one that has to then tell all the followers saying, write this entry to the log first. So long as the majority have then written, then the operation will be performed. Okay? So leader-based. Okay? And so there are two aspects. There's normal operation, and there's leader failures. And then, of course, there are node failures as well. And we'll look at how each of them work. Okay? The first thing is leader election. You have to first select a RAFT leader. Okay? We know how to do that. We are not going to look at it. Okay? If a leader crashes, you know how to select a new leader as well. Standard leader election does. So there's some leader election running in the background that always make sure there's one RAFT leader. Okay? So long as there's a leader, you will perform normal log operation replication, which is the leader receives requests, okay, from clients. It then appends it to his log, and then it tells all the other followers to also append that request to the log. Okay? But it has to detect inconsistencies in the log, as we will see, because a node may crash. It didn't participate in some requests that were sent by the leader. Node comes back up, some entries are missing. Right? Or maybe the node received a request from a leader. It wrote it to its log, the leader crashed. So some nodes have some entries from a leader, but not others. So there may be extra entries, there may be missing entries. We got to deal with those. Okay? So here is how we are going to handle them. Okay? So essentially, time is going to be divided into epochs or terms. Okay? Each term is basically the duration of one stable leader. Okay? So the x-axis is time. The blue things there are leader elections. Okay? So that's when leader crashes, you elect a new leader. The green is basically the term of that leader. That's when the leader is alive and is basically performing normal operation. Then there's a leader crash. There's a blue phase, you elect a new leader, and that's normal operation. So you will basically go between leader election and normal operation. And all the green things there are normal operations. Okay? And so we really care about the green because we know how to do leader election. So we'll see how to do that. Okay? So you have, again, a leader. Yes, so a server at any point can either be a leader where it's the one receiving requests, telling others. It could be a follower where it's passively getting information from the leader, or it's a candidate, which means it's participating in leader. Okay? We will again ignore this and we'll just look at leader and follower on the next slide. All right. So, yes, question. Oh, what is a split vote? Split vote essentially means that you have, let's say, network partition. So you did not get enough votes because the leaders also have to be elected by a majority in this case, right? So you might not have enough votes, so you might have to restart. Like if you had network partition, you can have that. Right? So very quickly, I think we know how to do leader election more generally, but this is how RAFT does it. So there's a timeout value. If you haven't heard from the leader within a timeout, you will say leader is dead. So you can assume 100 millisecond or 500 millisecond. So half a second could be a threshold. It says if you haven't heard anything from a leader in half a second, then you assume that the leader has gone down, which means the leader has to keep sending some heartbeat messages even if there are no requests to tell all the nodes that it is up. Okay? So if there is no leader, then you can run leader election. You can vote for yourself as the leader and say I'm the new leader, or you can run any other protocol. It doesn't matter which technique you use, but you will essentially run that leader election. Okay? Once you pick the leader, then this is what normal operation is. Okay? The leader will receive a command, okay? And then it's going to send that to all the requests, all the followers, excuse me, saying write that to your log. So you will see that this is how the log is essential. So you will use RPCs, by the way, to do this. So you will essentially say, this is the term of the green leader. It says change the value of X to 3, change the value of Y to 1, X to 1. At this point, we assume that the leader actually crashed. A new leader took over. So you will have now a yellow term where you got some entries, then you have a blue term that you got entries. Okay? So essentially, you want to make sure that a majority of the nodes have written this to the disk for you to essentially make progress. The other minority can catch up in the background. They don't have to have done it in real time. They can catch up. But so long as a majority get the request from the leader and write it to their log, you're done. Because you have essentially replicated the log on a majority of the nodes in the same order. Okay. Now let's look at what happens when there are inconsistencies. Okay. So here is an example of a leader having some log and the follower has some other log. Okay. You will see the leader has 3 green entries, and there's a yellow entry and there's a blue entry, which means that after the first 3 green entries, the green leader crashed. You pick the yellow leader and you pick the blue leader. Okay. And then there's a follower that comes along that has 4 green entries. Okay. The first 3 match with the leader. The 4th one is an extraneous entry. Okay. So what must have happened in this case is, as the green node leader was crashing, this follower actually got a 4th entry, but the others didn't get it. So then, and then the leader crashed. So then you pick the new leader and proceeded, and somehow this follower also must have gotten a network partition or something. But when it rejoins the network, it has an extraneous entry here, which has to be removed because that's not the actual log. So the log is the authoritative log is the one with the leader. So somehow this extra entry has to be removed from the log. Okay? And then here is a more general case where you will see there are many followers. Okay? And you will see there are many colors that indicate which leaders were chosen. Here is B has a follower that has only seen the green and the yellow leader. It's not seen the red and the blue. So it's missing a whole bunch of entries. Okay? And then you will see there's one here that seems to have seen a red leader that others have not seen. Okay? And then there's yet another here that seems to have seen a purple and a yellow entry, which are all extra entries. Okay? So what happens in all of these cases is you have to do what is called log repair. Okay? When a follower comes up and its log does not match the leader, all it has to do is the leader has the authoritative log, okay, that it has replicated. So you have to first find the most recent entry that matches. Okay? And then you throw out all the extra entries beyond that, and then you get the rest from the leader. That's called log repair, which is shown on the next slide. So you will see here, if you have, this is the first top one is the real leader. Here are 2 followers. One of them has missing entries, the other one has extra entries. Missing entries is easy. You make sure that the entries match, and then you ask for the rest of the entries from the leader, and you catch up in the background by writing them, and then your log is repaired. Then you have the same log as the leader, and you can participate in normal operation. Okay? Extra entries means you basically take the index and you try to go back in time to find the most recent matching entry, which is essentially entry number 3. Okay? Because that leader does not have any of the purple or the yellow ones that this leader seems to have. So you have to keep going one entry back at a time until you find a matching entry. You delete that entire portion of the log because the leader has not received it. And then, so that part is gone, and then you do log repair and get the rest of it. And then again, you will match the leader, and then you can perform normal operation. Okay? So if you have missing entries, get the rest from the leader. If you have extra entries, roll back. You do log roll back until you find a matching entry. Delete the rest of your log. Okay? So then your prefix is matching the leader, and then you get the remaining suffix of the entries from the leader, and then you repair it. Okay, yes, question. Okay, the question is there any scenario where you have a matching entry with the leader, but there may be inconsistencies before? That's your question, right? So that scenario should not occur if you are always going to follow this property where you have a matching entry and then you just get the remaining from the leader, and so then you have the same consistent as the entries at the leader, or your extra entries and you go back and you throw out the rest. So if you just perform this over and over again, there should not be an entry in the middle that is does not match, because the prefix always matches is the assumption in this case, because you are only trying to repair the suffix. And so if suffix is always repaired correctly, then that becomes a new prefix, and so you repeat. So that hopefully will not occur in this type of scenario. Okay. Any other questions here? Yes. Okay. Is there any particular reason why we are using RPC call for append entry? So RAFT just uses RPCs. You don't have to use RPCs, but it is using RPCs as its mechanism. The implementation of RAFT, you can use other things as well. Okay. I think there's a lab 3 extra credit question for implementing RAFT in lab 3. So if you want to get some extra credit point, this is what you will have to implement. A replicated log that is performing this type of write operations and log repair operations. Okay. But yeah, in that case, just to answer your question, you are not required to use RPCs. You can use REST messages, for example. Okay. Any other questions here? All right. So that's essentially we are done with both paxos and RAFT. Okay, go back and look at this material, because there are subtle issues there when there are failures that I kind of glossed over. But if you have a little bit deeper understanding, you will benefit, and you have to implement, let's say, the extra credit question in the lab and so on. If you have any questions about any specific details, you can ask on PIADS or come to office hours. Okay, so I'm going to be done with our consensus. I'm just going to talk a little bit about recovery, and then we'll move on. So recovery is the other part of failure, where now the node that has crashed has come back up. How are you going to bring it to a consistent state? We saw a little bit of that already. So that's what RAFT did when it was doing log repair. That was the recovery part, where it was allowing a follower to come back to a consistent state because his log had become inconsistent with the leader. Okay? But this can be true for anything, not just RAFT. Maybe a web server crashed. Like maybe in your lab 3, you actually have to implement recovery, where you have replicated the catalog server. One catalog server replica crashes. You are continuing to perform transactions on the other catalogs servers. So when the failed one comes back up, it will have an inconsistent version of the catalog. You have to actually perform recovery to make sure its version is consistent. Okay. So how are you going to do that? So you can use techniques like checkpointing or logging. These are the 2 techniques you basically use, where you periodically checkpoint the state, and then you can recover to a consistent state. Or you can essentially do what we did in log, where you keep a log. You can do log replay or log repair and so on. But whatever technique you use, you have to actually perform failure recovery once the node actually comes back up. Okay, so this is also something to keep in mind. We already talked about distributed snapshots. Okay, that was a way by which you could recover, where you can take all the nodes back to a consistent snapshot. So checkpointing of state is an important part of trying to do failure recovery. Many techniques use checkpointing. Others use logging. Okay, so there's these 2 class of techniques. Checkpointing means you go back to a consistent state and restart from that. Logging says you keep the entries in the log, and then if you recover, you see what you missed, and then you catch up. Right? So either you go back to a consistent state, or you have the failed node catch up to a later state. So one of these 2 techniques essentially have to be used for you to implement this failure recovery. We already talked about distributed snapshots in lecture 13, so I'm not going to go back to that, but just keep that in mind as one of the approaches to perform recovery in the more general case. Okay, so I'm going to end it here. We have done a little bit early. So we'll stop here and we'll resume a new chapter next time, which is going to be on the World Wide Web. So the theory portion of the, not really theory, but conceptual. I don't think it's a theory class. The conceptual portion of distributed systems is done. Okay, we started with clock synchronization, then we did mutual exclusion, distributed transaction, we did consistency, replication, failure recovery, consensus. So it's a fair number of lectures. Those are the core concepts. That part is done. Now we're going to go back to more systems implementation issues. So we'll talk about World Wide Web, then we'll talk about edge computing, then we'll talk about middleware systems, we'll talk a little bit about security. The next few classes that we have remaining, we'll come back to how do we apply all these ideas in real systems. Yeah, so we'll see various flavors of all these ideas that you see when you talk about all kinds of real world systems. Yeah, so that's what's coming next. We'll stop here today and then we'll continue next time. But before all of you go, I did want to make one announcement, which was also put on Piazza. So if you have not yet accepted the invitation for Lab 3, okay, please do that by tomorrow. Okay. The reason is that there is a bug in GitHub Classroom which is making repositories visible to some random subsets of students. Even though your repository is private, others can see it, and sometimes you can see others' repository. So we have to go up because the bug is not yet resolved. We have reported it. Others have also reported the same bug. We are manually going and removing any extra permissions that have gotten created by some buggy scripts in GitHub Classroom. Okay? So for us to do that, we need all of you to accept your invitation and create your repository so we can check that your permissions are right and fix it if needed. Okay? So please do that by tomorrow so that the TS can make sure everybody's repository is in a clean state as far as permissions are concerned and no one can inadvertently see someone else's code and things of that. Okay? So please do that, and the TS will go, they're already fixing whatever repos have been created, but for those who haven't done it, please do it soon so we can help everyone with having a clean repository. Okay? So that's what I wanted to say. So let's talk again on Monday. Okay? So we'll stop here today.